Welcome to all. For your information, this is BSK class 193, earlier live streamed on 7th October 2022. That is maybe 2-3 weeks earlier. That class is now reconducted. I will tell the reason. That day, when I took the BSK class 193 or columns and struts class number 3, 1 and 2 over, then again after 4 continued later, and even column is concluded now. The chapter is concluded. That day I was in my native place, which is a remote village. There was lot of network problem. Even those who attended live, they told on that day, sir, nothing is audible or fully blur. Even you can see there, the same class is uploaded earlier. I have not removed it. You can hear my voice there. Voice was somewhat okay, but visibility was very poor. And it is a very important class. So I decided I earlier promised it that I will re-record and upload it. So today I am uploading it. So you go through this class after class number, columns and struts class number 1 and 2, go through this class, then continue 4. And even that class also you can hear. Lot of things are told. See what I told on that day, I made it somewhere there, I made a rough note, nothing there. Some 7-8 points are written. Not much. And numerical part I noted down. See, if I take a class second time or any number of times, I will not tell same thing again and again. Or not same thing like that. I cannot repeat the same way because I come to the class with only a pen, that's all. And calculator, it is there. I never come prepared. Prepared in the sense that prepared means not prepared in the sense that not preparing for the class, not that way. I don't have to prepare for the class. Whatever comes to my mind, I will tell. It will be correct only. So, since I cannot remember what all I told on that day, extra explanation, but rightly I made a note. Therefore, I made a note here. See, one important point I written here. Also axis, I may forget it. I told a very important concept. How you decide axis. See, suppose bending this way, or bending this way, or twisting here, or bending this way, or twisting all. How you decide axis, I will tell in the end of the class. Okay, now start. Euler's buckling load for long columns. See here, both end pinned or hinged. Pin and hinge both mean same. Both end fixed. One pin, one hinge, or one pin, one fix, one free. Blue color is the elastic curve. PB is the buckling load. That is compression for the column. Some other reaction will come. I maintained it. See, now, here L stands for actual length. Remember, actual length. E stands for modulus of elasticity of material. I stands for least. This least I told so many times earlier and later classes. So, further more explanation of this least will be known to you later. PB is the Euler's buckling load for the column. That is the load at which the column will buckle. That is the least load at which the column will buckle. Now, for all these 4 cases, we derived the PB, pi square EI by L square, 4 pi square EI by L square, 2 pi square EI by L square, pi square EI by 4L square. All these are derived in class number 2. With the differential equation, I proved it. Now, you can go through previous class and understand the derivation. Now, know the result. So, these are the 4 buckling loads. See, from strength point of view, this is the strongest column because this will buckle at a very high load. 4. Next is this one, next this one, and next this one. Regarding this one, I will update it later, one more class if possible, where I will tell summary of the complete column and struts, Euler and Rankine, and with all the principles I may upload. Then I will explain more. Or further classes after class number 3, 4, 5, 6, 7, 8, 9 over, there I explained everything. So you can go through it. Now see, what happens is, the buckling load has got common term here. Pi square EI by L square everywhere. 1, 4, 2, 1 by 4. People do not want to remember at different numbers there. Uniform expression is required. Or it is better understood if you got a common formula. So what is done is you modify this one. See, I written here pi square ei by L square equal to pi square ei by L whole square. 4 pi square ei by L square is pi square ei by, take 4 denominator L square by 4 or L by 2 square. Pi square ei by L square by 2 L by root 2 whole square, 2L square. Now, if you see here, let in general Euler's buckling load for all cases be single term pi square ei by L effective square, pi square ei by L effective square, single term. Now, where for any end condition, little ink problem, I will rewrite it. The 2 has spread there. I do not want such things. Okay. I put little more ink than required, I think. Okay. Pi square ei by L effective square, that is for any end conditions. Now if you compare this formula with this formula, see here, pi square ei by L square, pi square ei by L effective square. L effective equal to L. L is the actual length. Pi square ei by L effective square, pi square ei by L by 2 square. So L effective equal to L by 2. Here L by root 2, here 2L. L effective is called effective length of the column, which depends on actual length and end conditions. So later summary I have given. If you want, I can give summary. You can see here, summary here only. See, if both are pinned ends, L effective equal to actual length. If both are fixed end, L effective equal to actual length by 2. One fix, one hinge means L effective equal to actual length by root 2. One fix, one free means L effective equal to 2 times L. So now, any column, Euler's buckling load PB. So now onwards, now general formula PB becomes pi square ei by L effective square. That is single, only one. Where I explained other things, L effective is the effective length of the column based on actual length and end condition. So what you have to do? Use this formula always. Use always this formula. When you require L effective, see what is the actual length of column, see the end condition, accordingly get the effective length and substitute. This is Euler's buckling load. Now there is one more aspect here. See, now one small point. Remember, for any structural member, cross-sectional area A, moment of inertia I, then one term called section modulus Z. It won't come here now. And one more will come little later. Radius of gyration R. You should know all these are strength supporting factors. Strength supporting factor means if you provide more value, it becomes more stronger. See here, A more. Sorry, here A is not there. I more, column is stronger. Later, area will come. If area is more, column is stronger. In bending, Z is more, column becomes stronger. Later, slenderness ratio will come, where L effective by R will come. R more, column will be stronger. So these are all strength supporting factor, will be explained one by one later. Now, pi square ei by L effective square, you get it now, on this basis. Now see, now one more thing. What is that ei? See, the term ei, that is a product, you should, see, I won't write everything here. You should write it. Product of modulus of elasticity of the material and moment of inertia of the cross section. Here, it is the least moment of inertia. The reason I already told earlier, I will tell again, further classes, it is told. Least moment of inertia of cross section. So, remember, here I means I minimum, one extra, because I least moment of I minimum I will write here. I means I minimum. Least moment of inertia of the cross section. Today only I will show you why I minimum is to be considered. This product of Young's modulus of elasticity and moment of inertia, it is called flexural rigidity of the cross section. So many people, they tell it is for the beam. No, it is a cross sectional property. Furthermore about this cross section and beam, I will upload other classes. So just for information I told. Okay. Now, this is the formula Euler's buckling load in general for any end conditions now onwards. But here one drawback, not drawback. L effective is there, I is there. I is in numerator, L effective in denominator. That means higher is the I value, column is stronger. But higher is the length, column is weaker. Common sense. See, when the length of column becomes more and more, it buckles very easily. When the length is lesser, it won't buckle easily. These all further classes very thoroughly explained. Because I am restricting myself to what I explained in class number 3. That's all. Otherwise, lot of things are told further classes. You go through it. Now, here one not drawback. Technically or more concept point of view, instead of this formula, a modified version is used where a term called slenderness ratio will come. I will tell how it comes now. Now, see. We have, this is the Euler's buckling load. This is the original, you can call original or derived formula. This is derived formula. Okay, now, see, PB equal to in general pi square E I. I means I minimum. I already told you I won't write. Divided by L effective square. We know that. We know that means I know that, you know that. I am surely knowing it. Hope most of you are knowing it. If not knowing anything which is required here, which comes earlier from engineering mechanics all, if I tell we know that, you have to agree, no other way. I equal to AR square. This is, everybody should know this one. Where I is moment of inertia, A is area, R is called radius of gyration. Radius of gyration of cross section. Of cross section. So I equal to AR square. Regarding R, I explain very thoroughly in engineering mechanics class what is the importance, physical meaning, etc. Here in column chapter, I cannot go back to engineering mechanics. Now, if I substitute that one, then your PB will become pi square E into I becomes AR square divided by L effective square. Or this becomes pi square E into A divided by, see, L effective R square, take denominator by R whole square. Now the term, see, R means always minimum R, I told you. So therefore here R is called radius of gyration, R minimum. See, I told I equal to AR square, or you can tell R equal to root of I by A. So R minimum, that is least radius of gyration of cross section equal to square root of least moment of inertia I minimum by A. Now the term L effective by R, this is a very, very powerful term. This will tell you how slender column is. L effective comes in numerator, R comes in denominator. I will tell you a little later. Is called very powerful term in structural engineering, slenderness ratio. Slenderness ratio for the column. This time for column, not cross section, for the column. That is, symbol is lambda. Lambda is the symbol, I used it. Therefore, remember now, I'll remove this one now. Therefore, slenderness ratio, lambda equal to L effective by R minimum. Actually, regarding minimum, I told in RCC or steel, you should not take minimum, applicable. But in strength of materials, we consider L effective constant with respect to both the principal axes. Further, I will not tell now. Okay. Is R. Now, see here. Now your buckling load becomes what? Therefore, now your buckling load PB will become pi square E into A by lambda square. This will very clearly tell that as A increases, cross section is stronger, higher buckling load will come, column will buckle. What is one? Is lambda here. Okay. Because that has gone inside. Okay. Column becomes what? As A increases, area becomes more, column becomes more stronger, but as lambda increases, it is in denominator, column becomes weaker, it will buckle at a lesser load. Okay, now I will explain this one. So, therefore, I will write now here, original formula is pi square EI minimum by L effective square original. Okay, now I will remove this one now. This statement I will remove. This also I will remove. L effective is called etc. I will remove. Or I will put summary here and also note more concept oriented or practical oriented or subject point of view, your buckling load PB can be written in other way as both are same, PB equal to pi square EA by lambda square, where extra terms which are not explained there, A is cross-sectional area, then lambda is, I will put once again red color for that one, lambda is slenderness ratio of column and that lambda equal to L effective by R minimum. Effective length already explained here. Again that square actually square. Okay. Effective length already explained here. Now R minimum is, I write here now, comma, L effective already over. See, I written here, L effective. Oh no, already over. Okay, let it be there. L effective is effective length of column. Let it be there. Effective length of column. And R minimum is least radius of gyration of cross section. Remember, R minimum equal to root of I minimum by A. Just check the camera. If anything is out of camera, I'll just check it, safer side. Okay, no, everything is okay. Afterwards, if I find that something is out of camera, I'd once again write it. Okay, this is the formula. Okay, now, what I will do is, this all I will remove. I will first go for application. 1 minute now, I will see what all I told there. IAR square, modify the formula, modified over unit. Okay, see, one small important is unit. This also I can remove, yes. This also I can remove. Unit wise, PB is the buckling load. Whatever unit you substitute, see, E, unit is force by distance square. I is linear power 4. L effective is linear power 2. If you substitute, it will come force unit. Or anywhere here also. Sometimes it happens, see, pi square E, force per linear distance square, area linear square. Lambda is unitless. It is a ratio of effective length to R. L effective is linear, R also linear. So remember, this lambda is always unitless. There is no unit for that one. Further about it, I told later. I will tell later only. Okay, now I will first take up, then further if I remember, I wrote A, I, Z, R, or N supporting, revised, okay, L revised over. Then I told on that, I made a rough note there in the corner. I told I equal to AR square. Axis pending, I remember, axis pending. Okay, unit I told you. Okay, now, one example. That class, what I took, one example. See, a column of cross section, how much it was? 200 millimeter by 60 millimeter is of length is of length, how much it was? 4 meter. 4 meter. Then one end is fixed, and other is free. Other is free. That is like an electric pole. You can tell that way. Now further, modulus of elasticity of material, for material, that is E for material, equal to 200 GPa. Anything further? That's all. Question is, find Euler's buckling load. Find Euler's buckling load. That's all, and that day I have done. Okay, now solution. You can use either this formula or this formula. Okay, 1 minute. See, suppose I use this formula. See, now consider Euler's buckling load PB equal to pi square EI. I means I minimum by L effective square. Okay, then you write here everything you have tried. E is modulus of elasticity, I minimum is the least moment of inertia, L effective is effective length. That all you have tried. That I can't tell here now. Start. E is already known. E equal to, and one thing, substitute everything in newtons and millimeter, so that buckling load will come in Newton. Okay, start. E. How much I told here? 200 GPa. 200 GPa is 200 10 to the power 3 MPa. MPa means Newton per mm square. Okay, that also over. Then I minimum, see, for that cross section, it is a rectangular section. One side is 60 mm, all dimensions in millimeter. Other is how much? 200. So there is one axis here, say XX axis, other axis here, that is YY axis. So therefore, for this cross section, I will do one thing. Actually, as per this formula, area is not required. We want only I minimum. So to get I minimum is I about XX or I about YY, among the two, whichever is least. Okay, now, actually that much not required, but text systematically solving. See, start. I about XX equal to, you should know for rectangle, if you want I about this axis, it is parallel side into the perpendicular side cube by 12. It is 200 into 60 cube divided by 12. Somebody may comment also, but he does not know that which is least. I know it. But this is systematic solution. I will explain later which is the least. 200, this I not noted down. 200 into 60 cube divided by 12 is 36 10 to the power 6. 36 3.6 divided by 1 10 to the power 6 is 3.6. Correct? Yes, 3.6 10 to the power 6. It is 3.6 10 to the power 6 millimeter power 4. Then I about YY equal to, YY is parallel side is 60 now. 60 into 200 cube divided by 12. That much you should know actually. It will come 60 into 200 cube divided by 12 is 110 to the power 6. 40 10 to the power 6. 40 10 to the power 6 millimeter power 4. Therefore, you can tell least moment of inertia of cross section, that is I minimum, equal to lesser is 3.6 10 to the power 6 millimeter power 4. Or those who can use common sense, this much not required. See, for this axis 200 into 60 cube, for this axis 60 into 200 cube. Undoubtedly that moment of inertia or moment of inertia about that axis, when the term you are cubing is lesser, that is least. So undoubtedly 200 into 60 cube by 12 is much lesser than 60 into 200 cube. So that is common sense. But here, since I am solving systematically, I wrote everything. Okay, over. Now that's all. Now lastly, what do you require? Lastly, you require effective length. See, L effective. For L effective, see the problem. One end fixed, other end free. Column length is 4 meters. So your column is having a length of 4 meters. See, this is the L. L means actual length. Actual length L equal to 4 meters. Now, further, for one end fixed and other end pinned, here other end free. Other end free, I already told you, you should write L effective is effective length. You should write it. L effective equal to, see here, one end fixed, other end free, L effective equal 2 times actual length. 2 times L equal to 2 into 4 equal to 8 meter, but we want millimeter equal to 8000 millimeter. Over. With this data, if I substitute here, just 1 minute. Just I'll check the space there because I do not want to go out of camera. Sometimes it happens after writing, suddenly goes out of camera. Okay, I think I can remove some of the statements here. Okay, I'll write here. Just 1 minute. Bear with me because there is nobody to help me here to tell whether clear or not clear. If it's a live class, usually I ask the students only, visible or not visible. They will comment. Here, not possible. Okay. Therefore, okay. Or I will do one thing. Available space I will do here. In the available space. Or I will use blue color. Okay. With this data, substituting buckling load PB equal to, okay, now start. Pi square into E 210 to the power 3 into least I is 3.6 10 to the power 6 divided by L effective square 8000 square equal to, it will give in Newton, pi square into 210 to the power 3 into 3.6 10 to the power 6 divided by 8000 square. 111.033 10 to the power 3 Newton, that is 111.033 kilonewton is the buckling load by Euler's formula. Okay, now just for information, I want to tell something here. See, I write small letters here. Just for information, see now. Instead of using least I, suppose by chance you consider higher I. Then what happens? Tell me. Then, just for information, your buckling load will come pi square into 210 to the power 3 into higher I is to 40 10 to the power 6 divided by 8000 square. It will come, why should I calculate? Previous answer divided by 3.6 multiplied by 40. It will come divided by 110 to the power 3. 1233.7 10 to the power 3 this much Newton, this much kilonewton. Now, just for information, see, I will show you a column. Imagine there's a column here. See, this side is 200. This is 60, thinner. When you apply load, the column will buckle like this. Or if I hold this way, in the cross section, column will buckle this way. It is impossible that column will buckle this way. Impossible. I will show you axis later. So it will buckle where resistance is least. See, this way. So if I use that formula, then you can tell when the load reaches 111.033 kilonewton, when you apply, that is around 10 tons, nearly a little more than 10 tons, column will buckle this way. Then, when the load becomes 1233.7, this is around 11 kilotons, that is 123 tons. Then, when the load becomes around 1233.7 kilonewton, that is around 123.3 tons, column will buckle this way. Possible. So, a column buckles this way, then you should tell, oh, someone want to buckle other way. I will stand up once again and start buckling. Possible? Impossible. The moment the load reaches what? 111.033, column will buckle this way. Other buckling is not possible because our definition I told you, buckling load is the least load at which the column will buckle. That is original definition. When least load at which column will buckle. So the buckling load is 111.033 kilonewton. So this is nonsense. See, this is nonsense. Okay, now further I'll continue. I'll go for other formula. First I'll slightly clean the board. Okay, start now. See, same example, find user's buckling load. See, now from here I am changing now. You make a note here. Just earlier, little earlier, we found buckling load by the formula pi square EI by L effective square. That is the basic or derived equation. Basic or derived equation. Now do one thing. Consider the modified equation. This is modified. Actually, not only modified, the practical oriented equation. Lambda is a very important. I will talk about lambda little later, after discussion is over. Consider actually in the further classes, class number 4, 5, 6, 7, 8, 9, all, so much is told about lambda. Go through it. I told only class number 3 I am what? Rearranging. Buckling load PB equal to C, pi square EA by lambda square. I already wrote because to save the time. Why waste time? Now E, just now I wrote once again. Young's modulus already over. A is now you require area, cross-sectional area, and lambda is slenderness ratio equal to L effective by R minimum. Start. Write the cross-section. Area 200 by 60. Get the area in mm square. R minimum is least radius of gyration of the cross-section. R minimum equal to root of I minimum by A. Now I minimum is Ixx or Iyy, whichever is least. Just now explained how to find Ixx, how to find Iyy. Least I is 3.6 10 to the power 6. With that substitution, R minimum becomes root of I minimum 3.6 10 to the power 6 by area 12000 equal to 17.3205 millimeter. If somebody asks me what is R for this question, I will not find I will just tell him 60 divided by root 12, 17.3205 millimeter. That is finer concept. If you understand further, if you study later or if you study furthermore and study the property of rectangle, then you will be knowing. But as an academic question or general concept point of view, you find it. Okay, R minimum over. Then, once again I wrote, one fixed, one free. L is the actual length 4 meter. For one end fixed, other end free, L effective is 2L becomes 8 meter, 8000 millimeter. With this substitution, your lambda becomes L effective 8000 by 17.3205 equal to 461.8804. This is very high lambda. Okay. Now with this data, I'll use a different color here, maybe red color. So change it. Substituting Euler's buckling load PB by the modified formula is pi square into 210 to the power 3 into not I into area 12000 divided by lambda square 461.8804 square. Everything is in newtons and millimeter. Answer will come in Newton. That is, you tell the answer kilonewton. I don't have to calculate. What was the answer? 111.033. 111.033 10 to the power 3 Newton. It has to come 111.033 kilonewton is the answer. This will be the buckling load PB by the modified version. Okay, now little time on that class I told little more about slenderness ratio lambda. I will tell it now because on that class I told it. Searching for the paper here. Okay, this all I will remove now. Okay. Nothing required now. Axis, now I remember axis. Okay. Now I remember the axis. What all I told in class number 3, I will briefly tell now. See, lambda, that is slenderness ratio, equal to L effective by R minimum. This R minimum I told in RCC steel, some corrections will be there, that not required here. See, this is the ratio of effective length. See, effective length means it connected with the length. Where is my scale? Which I used to buckle here. See, effective length this way. And R minimum is root of I minimum by A. Remember, R minimum is cross-sectional property. I will give a small important for you. You should understand, because understand by only earlier concept. If you remember CGMI part, or what I tell you believe, it is connect for rectangle section, or usually, no, not usually, always R minimum depends upon the thinner side, where weakness is there. See, now, furthermore, I told you, furthermore, thoroughly I told later. Later means other classes. See, buckling is very easy. Why? Buckling becomes very easy, or column is very weak when L becomes more, or R become lesser, or when the length increases and cross section becomes thinner and thinner. See, length increases, cross section becomes thinner and thinner. It's a bad case. Column becomes very weak. So, as length increases, see here, as L means L effective. As L effective increases, or as R minimum decreases. L increase means column becomes more and more longer. R minimum decreases means it becomes thinner and thinner, becomes very weak. Then lambda will increase. Lambda will increase, and finally, if you increase beyond the limit, it will become a slender column. Slender is a bad word. See, slender. See, you tell slender means what? Weak. So that's why it is called slenderness ratio. Now, practically, it is better not to have high lambda. Lambda high means column becomes weaker. So when you design, you should give sufficient cross section so that lambda is reduced. Because L you cannot do anything. Column height you can't do anything. It is not in your hand. So therefore, to control lambda, only solution is what? Provide higher cross section. And now see, or as L effective decreases and R minimum increases. That is, length becomes lesser and lesser, column becomes bulging this way. See here, I'll show you. Length reduces and column becomes what? Thicker. See here. Length reduces, it becomes thicker. Now you can't buckle easily. It has got high strength in buckling. It cannot buckle so easily. Then column becomes what? Lambda will decrease. Lambda will decrease and it will try to become a short column. Here, slender means it will tend to become a long column. Then there's an intermediate term called intermediate column. That all I discussed later with the examples. That's all I told in class number 3. So remember, length increases, cross section becomes thinner and thinner, column becomes weak, lambda increases. That's why it is called slenderness ratio. Length decreases, column cross section bulges stronger. This is regarding lambda. Furthermore, I won't tell because this is actually class 3 what I told. Okay, now, lastly, one small important point. This is regarding the axis. I saw that recording. I saw the video of that class. Then I suddenly I made a note. Oh, I told axis there. So I will tell you here now. See, how you decide axis for bending. See, buckling is actually nothing but bending only. See here, it is nothing but bending. I will not take much. First, I will tell you basic definition in physics for rotation. See, rotation is this way. Bending also finally that way only. Bending is little small. Rotation means this way. So, physics definition. A body is said to be rotating about an axis if each and every point or element, anything in the body remains at constant distance from that axis throughout the rotation. See, now if something is rotating this way, see, this is the axis. How? See, if something is rotating this way, this is the axis. See, or if something is rotating this way, this is the axis. In my class, I ask students, tell the answer. They will tell, see, I will show this way. Rotation, show axis. Sir, yes, correct. Now, they will tell, sir, this way, correct. Now, this way. How, in what way, suppose you draw a circle in a plane, perpendicular to that one is axis. See, this way. Now, when bending takes place, see, when buckling takes place this way, or when the structural cases, axis comes in the cross section. So what you have to do is, see, buckling this way. See, this way, this way. So you continue your hand, you slightly buckle, then continue. See, axis comes this way, means this is the axis. See, if buckling is, this is for this buckling, this way it cannot buckle, but I will turn it now. See, if buckling is this way, this is the axis. If it is twisting, see here, if you twist, then axis is like this. Furthermore about the axis, I usually tell when the time comes for that one in the advanced course, I will tell. Time being, lastly remember, see, this way remember, axis, 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 or bending this way, bending this way. This way, for column. Axis. See? This axis. Okay. Go through this class. What problem was there for that class number 3? I know I have gone through the class. Very horrible it was. It is, for so many would have cursed me. What is this class? What you can make out? Nothing is audible or nothing visible. Okay, now I made the class once again and uploaded now. Therefore, you go through this, you consider this is the official class number 3. And just for understanding more, you can go through that class and listen what I told. Don't see the board. What I told, points or maybe some extra point I told. You can go through it. Some jokes also I told on that class about buckling, some electric shock, something like that. Okay, that you can go through that one. So this will become official class number 3 for columns and struts. Okay, thank you.